Hi everyone, welcome to a new video. This is the first part of this two-part series about garbage collection in Golang, where we will talk about what garbage collection is, why is it needed, when is it triggered, how is it triggered, some Golang specifics about garbage collection. We'll also talk about the algorithm underneath that garbage collection is using, and we will also write some sample programs so that we can see how practically garbage collection works in Golang. So let's get started. So let's start with what garbage collection is. So whenever we create programs, if we talk Go specific, then we create these data structures like structs, slices, maps, simple variables, etc. And when we run those programs, it will constantly allocate memory for all these data structures. And if we have a decent size code base, a lot of those data structures are just needed temporarily and they are not needed afterwards. So if we do not clear them from memory, that basically means our program is consuming more memory. So if we are not freeing the unused memory and our program keeps on leaking memory, it may eventually crash. And that is what garbage collection does. It clears out the unused memory. Let me show you a small example on this. Let's create a node object. Let's say it has a value and it has a pointer to the next node. And here we will create A, which is a node with value 1. Then we'll create B, which is a node with value 2. Then we'll create a variable C, which is a node value 3. Let's say A, next node is B. Oh, I just saw that we are creating structs. I actually want it to be a pointer. So A is pointing to this particular value, B to this particular value, and C to this one. So now the first node points to the second node, or the first node holds the pointer to the second node. Similarly, the second node holds the pointer to the third node. So now this looks something like this. This is main. It holds A, let's say, and A holds the pointer to B, B holds the pointer to C. Let me comment it. What the hell? So this is a perfectly valid case and there is no garbage collection needed in this case because we are actually using everything over here. So none of the memory is unused. So we would not want to clear any memory in this case. And GC in this case will start from main. It will see that A is reachable, from A, B is reachable, from B, C is reachable. So it's not a problem. We will not clear out anything in this case. But what if later on in program we do this is equals to nil. So now it's something like this. C here is pointing to the address in memory, or C is the address in memory where this particular value is stored. But do we really need this value? We are not using it anywhere. So in this case, we can say C is just doing nothing. It's just floating. So what happens is, in this case, GC will clear out the value of C. And how GC is going to do that is, it will check from main, A is reachable, B is reachable, but C isn't reachable. So it will clear out C in that case. If I show you another example, let's say we have this function temp and it returns, let us say, node, and it is going to return a pointer or address of node with value, let's say 1. I removed the struct itself. Value. Now in main, let me call temp and let me say a is equals to temp, and then if I say a is equals to nil, what is wrong? Declared and not used. So let's say fmt dot print a. Now in this case what happens is we are calling this, so this is called and this creates this particular value in memory, and a is pointing to the address of this particular value. But if you look carefully, what happened is, it's like in memory we created this place, this node that we created, value 1. This is stored in memory. Where is text? Let me zoom in. And then a is pointing to this particular value till this point. But later what we did was we said a is equals to nil, so a is not pointing to this particular value anymore. So do we really need this value? If we don't use GC, this value will be stored in memory forever, and this is never going to be used anywhere. And that is why we want GC to clear it out as soon as it is unused and is not going to be used anymore. So that is the whole point of GC. How GC does that is, like I said, it checks what is reachable and what is not. We will talk about this in detail later on, but if I have to give you some idea, it basically checks, see, from main, A is reachable. From A, can we reach temp or this particular value? Yes, we can. Can we reach it now after this is run? No, we cannot. So after that point, what happens is it will basically clear this value out. So that is the core idea, reachability. GC will check that if the piece of memory can be reached like from your running code directly or indirectly through chain of pointers, like we saw in the earlier case. A was pointing to A, hold the pointer of B, and B had the pointer of C. So everything is reachable. So the idea is that if a piece of memory is reachable from your running code, either directly, let me go back to the code and it will be more clear. So here, if the piece of memory can be reached directly, which is the case here, that A, B, C can be reached directly because we created them here. Or they can be reached using chain of pointers, like we said. Like here, A can reach B and B could reach C, but we did nil here, so we cannot reach C in this case. And if we cannot reach C, GC will basically clear its value out. And if we don't do this, then the unused memory will keep on piling up, which is what we call memory leaking, and eventually your program is prone to crashing then. Now let me give you some more details on where GC works and where GC doesn't work. As in stack, which is what GC doesn't care about, versus heap. I assume you have some idea of stack and heap. I'll not talk about detail of stack and heap here, but what I want to say is that GC doesn't care about stack. It only works on heap. Why? Because in stack, whenever a function is called, at that point of time, memory is allocated, and whenever the function will return, the memory will be automatically freed, right? So in this case, we don't need GC. But in the case of heap, it is a shared, it is not function specific, it is a shared and longer lived memory. And if it is longer term and it is something that is not specific to functions, so it's like if something is outliving a function, any piece of memory is outliving a function, then it is part of heap. In that case, we would want to make sure that yes, heap is not storing anything that is unused. That is why GC only works on heap. So if I show you a very small example, then let us say an add function. Oh, so we didn't return anything. And so this is basically for stack. So this R value that we see, it lives in stack, and as soon as this function is, as in we call this function and we get the value when the function exits, as soon as that happens, stack will be emptied. This is not accurate, so it's like if I call in here, so as soon as this result is returned, or this R is returned, this is where the stack will be emptied. So in this case, like the stack and the heap both are part of RAM, and the idea is to save RAM, as in don't store stuff on RAM which is not needed. So in this case, anyways, stack got emptied, so the RAM is now back to normal. We allocated this, it returned, and it is back to normal. It is, this particular piece of memory has been wiped, so it's not a problem. Hence, we don't need to take care of garbage collection in stack. But in the other example, like we had earlier also, we were calling it temp, and let's say it returns this node. Or let's say node is equals to this node with value 1, and we will return node. And here I will call x is equals to temp, and for now I will just print x. So in this case, what happens is this particular value that we have created, or this piece of memory, will be alive as long as x is there. And if we don't do GC on this, this will be alive forever, as in this will be in the RAM forever, and it will not be cleared. As of now, it is being used, but let's say x is equals to nil. And in this case, now x is pointing to nil, so it is not actually pointing to the same case that we did here, right? X, let's say this is x was pointing to this particular value, and it is not pointing to this value anymore, so this is actually not needed. That is why we only care of heap in case of garbage collection. Stack already takes care of itself. For heap, it is shared and it is longer lived, so in that case we need to make sure that okay, if something, if any piece of memory is not reachable anymore, we would want to clear it out. And for now, that is all we will talk about stack versus heap. If you want to learn more, there are much more interesting stuff. And there is very interesting thing about Golang Go routines. It's like each Go routine that we create gets its own very small stack. It's like 2 KBs. and it dynamically grows, which is what is amazing about Go, that Go's concurrency is dynamic, as in if we create a Go routine, then it has a dynamic stack associated with it. If you cross 2 kbs in that stack, then it will dynamically grow. Whereas in other languages like C or Java, in those languages, there is a fixed stack. I think it is something like 2 megabytes or 1 megabyte, something around that. But it is static. It cannot dynamically grow. So if your thread, we create thread in those languages. If your thread reaches that particular capacity in that particular thread, then it will crash. So this is a very interesting thing. You can read more about it. But let's move on with Golang GC. Now let's talk about the tricolor mark and sweep. I had a diagram for that. So this is basically the algorithm that GC uses to clear out the unused memory. What happens in this case is we have like 3 colors. That's why it's called tricolor. Let me also write it down. Tricolor mark and sweep. So this works on 2 phases. The first phase is mark. The second one is sweep, which is basically clear out whatever is not marked. So what basically happens is it has 3 colors. I'll copy this actually. White. Not necessarily, as in these colors are just for representation. These are not actual colors that are implemented in the algorithm. You can call it anything. You can change the colors, doesn't really matter. This is just for representation. So basically what they represent is white represents that this is unreachable, or we can say not visited. I need to zoom out a little bit. Not visited, most probably unreachable. Gray basically is the ones that can be reached. And black is that they can be reached and their child, let's call it child, that their children is gray or reachable. So this is basically the idea. Let's see in this diagram. So it's like initially everything will be white. So we will say that all of these are not visited, right? And let's not say most probably unreachable, because we have just started yet. So these are white, basically means not visited. So these are the ones that are not visited yet. And then we start from the root variables. Root variables are nothing but like the global variables or the current stack variables. So this is the first variable. So these guys have marked it star. So let's call star as black. So in this case, star is black, and then gray is actually black. It's confusing. Actually, let's do it this way. Let's call it black, and let's call this one as star. We are just trying to match this with the diagram terminologies. So it's like the first one that we reach is at, actually this should not be star at the beginning, this should be gray because we are going there for the first time. So gray is basically the root and it is reachable. And then in the second step, they will say gray is reachable, it has children. So what we will do is these two children. Let me zoom in a little bit. So it's like this is gray as of now. And these two children are reachable. So that means we can call this star, like we have said here, that black is the one that can be reached. So initially this becomes black because this can be reached. But in step 2, it will become a star. Why? Because these are the ones that can be reached and their children are gray. So we reached here, we made it black, and then let me do it on this. So this is black, for example. And why is it not black? Come on. Oh, it's white actually. Yeah. So first this will become black and that's it. That is the step 1. And then the step 2 is that it will check, okay, which of these are reachable. This one is reachable. So this becomes black and this becomes black. And since this node or whatever you call it, it has its child as black, it has its children as black, hence it is now a star. Oh no. So I'll just move it. Something like this. If I show you again, black is basically the ones that can be reached. So these are the ones that can be reached, and star is the one that can be reached and their children is gray. So since their children is gray, not actually gray, it should be black now. So its children are black, hence this becomes a star. And then the next step would be that this becomes a star and then all these are covered. This becomes a star and all these are covered. So this way, if we keep on going, we can clearly see that all of these will be marked, and whatever you call them, you can call them star or you can call them black. But the idea is all of these will be marked. And since this, all of these are unmarked or white, that is where the second phase starts. When all of them are marked and we cannot mark others, we start sweep. Sweep basically means whichever ones are unreachable, whichever pieces of memory are unreachable, just clear them out from memory. So this is basically the algorithm behind GC, and this is how GC actually works. And I have showed you in code as well that how it checks for unmarked. This is what exactly happens under the hood. Now let's talk about one more important thing. How do I write? Why am I not getting text? Oh, so it's white, it's black in color, that's why. Okay, sorry for that. Clear all of this. So let's talk about when GC is triggered. So another beautiful thing about Golang is that we don't have to manage garbage collection on our own, which is what we have to do in languages like C. So in Golang, most probably you will not have to manually trigger the GC most of the times. it will be done automatically by Go. So GC is an automatic process in Go. Now, when does this GC, or when is this GC actually triggered, even if it's automatic? So the idea is that GC will be triggered every time whatever the first GC or the previous GC cycle's heap size was. If it grows more than that, then GC will be triggered. The initial heap size is something like 4 megabytes. So if 4 megabytes in heap is reached, then GC will be triggered. It's like so let us say this is your heap, and when the program starts, it starts storing memory. So it keeps filling and it keeps filling, and it gets filled till 4 megabytes. So that is the initial trigger for GC, and garbage collection starts in this particular threshold. And then what happens is, let's say it could clear out some unused memory, and now the used heap is not 4 megabytes, it's actually 2 megabytes, because we could clear out a few unused pieces of memory. So now it's 2 megabytes actually. So this is the current heap cycle after the first GC run. We will just twice it, and that will be the threshold for the next GC run. So it's 2 MBs. So now the program keeps on continuing. The program is running. Again, a few things are stored in memory. So the memory keeps on being allocated. It keeps on filling the heap. And since it was 2 for the first cycle, now when it reaches 4, so for example, now it has reached 4 megabytes. Now the GC will be triggered again. It has reached 4 megabytes. Now let us say GC is triggered again, and we could clear out a few more pieces of memory or few more objects that are living in memory. And now it became 3. In the second, by the end of second GC cycle, it is now 3 megabytes. So now the threshold will be 6 megabytes. So the next GC run will be on 6 megabytes. So now again the program continues to run. It keeps on filling up more heap, and when it has reached 6 megabytes now, that is where the next GC will be triggered. And let us say it could clear out a few more things, and then it became 5 by the end of the third run. So the next threshold will be 10 megabytes. So that is basically the idea, that GC runs whenever the heap size doubles from the last GC cycle. And obviously if it is not doubling, then should we not clear the unused memory? We should, right? So it's not just about let me write it down. Oh, what the hell, I'm writing something. How do I remove this? So GC is an automatic process in Go. It is triggered when the heap size reaches the double of the heap size in the last run or last GC run. Now the thing is, even if the GC size or the heap size has not reached the double, should we not be clearing out all the unused variables in memory? Obviously we should be, right? So GC will anyways run periodically as well. So it's not just that if we reach the double size of the heap size that was with the previous GC cycle, only then we will clear the memory. We will clear the memory periodically every X minutes. I think it is 2 minutes. So this is when GC is triggered. If we want to do it manually, then also we can do it using, we can trigger the garbage collection via runtime package. So this is a standard library in Go, runtime, by which we can control GC. So you can run the GC using this command, runtime.gc. And you can also use runtime.gc to change this particular threshold. So if you do not want that GC only runs when the heap size is twice the size of heap size of the previous cycle, you can change this as well by using the GOGC variable. So this GOGC is basically just an environment variable. You can set it. If it is default set to 100, so that means after 100% growth, which is twice the size of previous heap size, it will run. If you want to make GC or this GOGC as 50, then it will be 50% of the growth. So it's like if the current is like if the initial heap size when it was triggered was 4 megabytes, and after the run it was 3, or actually it was 2, let us say, then 50% of 2 is 1. So if 1 more megabyte is added to the heap, they will run the GC. So this is basically the idea of when GC is triggered. So we talked about what GC is, why it is needed. We also talked about how GC is working, what is the underlying algorithm that GC uses, and we also did some basic Go programs to see how actually GC is triggered. This is it for this video. So in the next video, we will talk about a few more concepts. We will continue this. So we will write a few more programs and see how we can trigger GC ourselves and how it actually works in the program itself. And we will talk about GC pressure, what GC pressure is, and what are the factors contributing to GC pressure. So this is it for this video. Thank you for watching this, and I'll see you in the next one.